So sometimes the volume method we just saw won't always work out well. Sometimes we're going to have to use a slightly different method of finding our volume. So say we wanted to take a look at finding the volume of the solid obtained by taking this region here and rotating it about the y-axis. So if we rotate it about the y-axis, essentially we'd take and copy this shape over on the other side. You can try to imagine it rotating around this axis, and we would normally want to kind of have some sort of inner circle at this point and some sort of outer circle to work with. And here we've got our function is y equals 2x squared minus x cubed. Now, since we're rotating around a vertical axis, we want to integrate with respect to y. So here we would want to solve for x. So this means solve for x. But if y equals 2x squared minus x cubed, we can't solve for x. So, an alternative way to look at volume problems sometimes is known as the method of cylindrical shells. And for this example, it'll be easier to use. So how do we think about cylindrical shells? Well, say we've got something that looks like a cylinder, but we got the middle part of the cylinder taken out. Well, one of the things we can do is we can look at having an inner radius R1 in this picture. R2 here is the outer radius. It's got a height of h. And so if you want the volume here, you'll take V2, which is going to involve radius 2, minus V1. So this would be the outer cylinder, and this would be the inner cylinder. Which means that our volume would equal pi r2 squared h minus pi r1 squared h. But we can actually rewrite this in a way that'll be a little bit easier to work with. We're going to rewrite this as the volume will equal 2 pi r h times delta r. So here, what we're actually going to think about doing is we're going to think about this being the circumference of some sort of object. So we've got circumference here. Here we still have our height, and this delta r will be the thickness of the shell. So if we think about this, if we looked at one of these circles here, essentially if we went around the outside, there would be some sort of circumference formula that we could find. And then we'd have a certain amount of height for those. And then each shell that we'd look at would be delta r thick. So we just have to figure out the circumference, how thick it is, and the height, and multiply those together and figure out what we are looking at overall. Now here, we're going to have that delta r equals r2 minus r1 from above, and r here is going to equal r1 plus r2 over 2. So in general, what we'd be thinking about doing is if we wanted to do this rotation, we'd essentially look at taking a large number of these cylinders kind of next to each other. So we'd have maybe a center cylinder, a cylinder next to that, and their heights would be changing as we kept going. And so what we could do is we could find a new way of formulating our volume using all this. So say we've got a solid S obtained by rotating about the y-axis, the region bounded by y equals f of x, where f of x is greater than 0, y equals 0, x equals a, and x equals b, where b is greater than a is greater than 0. And we wanted to find this volume. The volume here is going to be the integral from a to b of 2 pi x times f of x dx. So in other words, you can think about this as being the circumference part, this as being your height, and then because we are doing our integration, we're essentially doing that infinite sum. So because we're doing that, we don't have to worry about the delta r portion. That gets taken care of in the infinite sum. So the easiest way to remember this formula is to think of a typical shell cut and flattened with radius x, circumference 2 pi x, and height f of x, and thickness delta x over dx. Essentially what we're doing here is for each of these shells, if we flattened out what we had, we would have a rectangle of some sort. And you can see my drawing skills are some of the best. And essentially we have one side that is 2 pi x, some sort of height f of x, and then however thick this would be our delta x. And so essentially we're just taking this, flattening it out, and turning it into a rectangle, and using that. And so essentially then we're finding the area of a rectangle, or the volume of a rectangle. So say we wanted to use this to go back to that first example, and find the volume of a solid obtained by rotating around the y-axis, the region bounded between y equals 2x squared minus x cubed and y equals 0. So essentially we start off like this again. So we'd start off with y equals 2x squared minus x cubed. We know y equals 0 is going to be one of our boundaries. So we want to basically figure out where this intersects 0, so that way we know where all we are looking at for this region. And then we are rotating it around the y-axis. So here, the things we need to know are our circumference and our radius and our height. So here, the radius is being found by the x part here, and so that's part of the circumference. So we can think about the radius as being this distance here, x. So the radius is x, which then informs us that our circumference is going to be 2 pi x. Now we need to know where we're integrating to and from, but what we can see is that our heights here are going to be f of x, which is just 2x squared minus x cubed. Now we want to know where we're integrating to and from. It's pretty clear here that y will be equal to 0 when x is 0, but when else? So if we use this, we set 2x squared minus x cubed equal to 0, because these are our two equations we're looking at. We get x squared times 2 minus x equals 0. And that tells us that x equals 0 and x equals 2 are our places we need to be concerned about. So 0 and 2 are where we're integrating to and from. So that means if we want to find the volume will be represented by the integral from 0 to 2 of 2 pi x times 2x squared minus x cubed dx. So here we're just interested in, at the moment, setting these up. So again, we've got our circumference times our height, and that is how we get the volume using this method of cylindrical shells. All right, let's look at another example. Say we wanted to find the volume of the solid obtained by rotating around the y-axis the region between y equals x and y equals x squared. Okay, so now we're looking at y equals x and y equals x squared. We should end up with this portion. And so the questions that we want to use, we could use a washer here. But say we want to use this method of cylinders. So say this is a method that we want to use. Here the radius is, again, if we're going around this, going to be whatever the distance is in x to this point. So the radius is x, and that tells us that the circumference will just end up being 2 pi x. But notice that if we want to look at the height of each of these pieces, this portion here will be the height. And how we find this height is we take the bigger piece minus the smaller piece. So our height is going to be x minus x squared. And again, we're integrating from 0 to 1. So that means our volume will be equal to the integral from 0 to 1 of 2 pi x times x minus x squared dx. And again, right now we're really just interested in if we can set this up. Although, if you go through this, this was one of our examples, I believe, from the previous set of notes. Let me just kind of pull that up again really quick. It looks like this was example... This is why you put your pages in order when you go to put things away. No, this is not one of our examples. Never mind. But if you wanted to use washers instead, you can check to see if you get the same final answer. So, could use washers instead. Set up both ways and see if you get the same final answer. As a little bit of a hint, you should get the same final answer. If you don't get the same final answer, definitely talk about it in the discussion boards. Start having some back and forth and some questions about, how can we set this up to make sure we're getting the same thing either way. Now we also could use this if we wanted to go ahead and rotate about the x-axis. So say we wanted to use the method of cylindrical shells to find the volume of the solid obtained by rotating about the x-axis, the region under the curve x equals y squared, from x equals 0 to x equals 1. So here, what we're doing is we want to look at x equals y squared, which will look like this. We want y to be greater than or equal to 0. So say we get to 1 on the x-axis. So that'll be where we stop things off. And we're taking this region to make our shells. And we're rotating about the x-axis. So if we rotate about a horizontal line, with shells, we will integrate with respect to y. So if we want to find our radius, what we're going to do here is we're going to go ahead and have our radius be equal to our right function minus our left function. So in this case, here is our radius, and it ends up being equal to 1, since we have this solid line of 1 here, minus y squared. And this means that our circumference will be equal to 2 pi times 1 minus y squared. Now the height of these is going to just be equal to y. And so what this means then is that our volume will be found by taking the integral from 0 to 1 of 2 pi times 1 minus y squared times y dy. All right. So let's go through one more example, and then we'll kind of talk about some guidelines you're going to want to go through. So say we wanted to find the volume of the solid obtained by rotating the region bounded by y equals x minus x squared and y equals 0 about the line x equals 2. So again, we need to know where these intersect. So that way we know what our bounds are going to end up being. So here we'd want y equals x minus x squared and y equals 0 to intersect. So if we have 0 equals x minus x squared, then 0 equals x times 1 minus x, which means that x equals 0 and x equals 1 are our points of intersection. So we'll have, these are our functions. Here's 0, here's 1, so here's 2, Probably not drawn perfectly, but that's okay. So we want to go ahead and take this region and we will treat it as though they are shells. And we're rotating along this line. So here, when we are doing our method of shells, the radius is going to be the distance between here and here. Whatever this distance is our radius. And then from there, say that we want to use this portion here, we would then figure out the height with this. So this portion is the radius, then we have the height. So our radius is actually going to be 2 minus x. So say we had x was 0, the radius would be 2. If x is 1, then we have 2 minus 1 to get 1. But if it's somewhere in between, say it's 0.5, then it's 2 minus 0.5 and we get a radius of 1.5. So then our circumference ends up being 2 pi times 2 minus x. Now our height, normally we'd worry about being the top part minus the bottom part. In this case, the bottom part is just 0. So we'll have x minus x squared minus 0, or just x minus x squared. So that means our formula for the volume is going to be the integral from 0 to 1 of 2 pi times 2 minus x times x minus x squared dx. And when you end up solving this, you should get pi over 2 as your volume. So I want to actually go back to the previous example and make sure we're understanding why it is we are getting what we're getting. So here, for this example, when we wanted to find our radius was from the line we were integrating to where we ended up. And so when we take a look at this example, we want to look again from where we're going to where we're ending up. So that means that when we're looking at this,